Hello there, how's it going? I'm Masahiro Toyota, and I'm now sending this message from my office at Osaka Prefecture University. The world is getting nervous about COVID-19, so I decided to give my final lecture on video like this way. It can't be helped, 仕方がない in Japanese. First of all, I'd like to introduce some very nice messages from my friends who are world famous professors and chemists. Okay, let's get the ball rolling. Here we go.
Hello, let me first introduce myself. I am Françoise Colobert, professor in molecular chemistry at the University of Strasbourg in France. It's my great pleasure to say a few words about Professor Masahiro Toyota. I met Masahiro and his partner Katsuko for the first time in Strasbourg when he was visiting professor in Rouen. Rapidly we felt friendly together, and I enjoyed very much his personality and the discussion we had about chemistry. Then I had the chance to meet Masahiro and Katsuko many times in my life in Strasbourg and Osaka, and we became very good friends. Masahiro is a fantastic person, and every time I enjoy his personality. He loves France and Strasbourg as much as I love Japan, and of course we share the passion for chemistry. Thanks to Masahiro, I had the chance to be invited professor 3 times at Osaka Prefecture University, and it was each time a really nice experience shared with Masahiro and his partner Katsuko. They learned me a lot about the way of cooking in Japan, particularly the nabe recipe. It's a kind of chemical advices. Each time their warm welcome left me with excellent souvenirs. Masahiro was also invited to the University of Strasbourg as visiting professor to teach and chair chemical project with me. He is also the ambassador of an exchange student agreement between OPU and the University of Strasbourg, and this agreement will be signed within a few days. As I already said, Masahiro loves the city of Strasbourg, and more particularly the antique shops and markets in Strasbourg. We have rare occasion in our life to combine job and friendship, and with Masahiro and his family it was each time we met together a great complicity. I will also retire in the near future, but I hope that we will have the occasion to meet each other again in France or in Japan.
This is Ulrich Kurt from Marburg, Germany, contributing to Masahiro Toyota's retirement. Dear Masahiro, retirement means the end of duties, not of interests. Your duty to teach and supervise students will come to an end, but your interest in chemistry, in particular organic synthesis, can and will continue. Vladimir Prelog once said, Studium chemiae nec nisi cum morte finitur. I send you my best wishes from Marburg to Osaka. By the way, retired professors are still allowed to travel, and I would be happy to welcome you in Marburg in the future. Stay in good health and mood, Ulrich.
Okay, hello, Masahiro. It's a pleasure for me to send you this message from France at the occasion of your retirement. So organic chemistry is a real game for us, and it allows the possibility to build very complex molecules that's never been synthesized before. We can also try to build very complex structure step by step by mimicking nature. I think during your career, you were interested in this subject to reach natural products, and you developed very elegant methods towards the synthesis of complex structure like serofendic acid, micalamide A also. And I remember your lecture you gave here in Lyon, for us, of course, and also for our students, and they learn, I'm pretty sure that they learn a lot about the use of palladium chemistry, because you are an expert in this domain. I should mention also that you have developed a new project, which is known SynthUp database, and this project was really important for the future. So I think you are a pioneer in artificial intelligence, and that's the way for the young generation. Okay, so I think we meet together in 2012 or something like that. And shortly after, you were able to come here in France to visit us as a visiting professor, and also to deliver some lecture also in different places. And it was quite interesting, of course, to discuss with you, not only on chemistry, but also on gastronomy, which is a famous subject here in France. I had also the privilege to come here at OPU, thanks to your invitation, and I discovered also Japan. It was a real pleasure to come in your beautiful country and to discover a lot of new things for me. It was possible because it was so kind to invite me. I really appreciate, and thank you again for that. So it's time probably to wish you all the best for the new adventure just after the retirement, which is not just the beginning of a new aspect of the life. So I wish you all the best for you and Kazuko, and I wish that we could meet together once again, at least once again, here in France or perhaps in Japan. Okay, so Masahiro, cheers, and see you soon, perhaps. Cheers.
Hello, my name is Jacques Medalino. I'm a research director at CNRS in France, and I'm very happy and very proud to be invited to distribute to Professor Masahiro Toyota upon the occasion of his retirement from Osaka Prefecture University. Masahiro has been a friend and a colleague, and I really appreciated all his help during the time we've been collaborating. He has been hosting me as a visiting professor in the frame of the hetero program of Osaka Prefecture University, and this has been a wonderful time that I really remember and enjoyed, and I'd like to express him all my thanks for that. He has also been a wonderful guest when he came to Rouen University in Normandy, where he has been staying for 1 month, and he has been very helpful by exchanges and discussion with people. He has been hosting several students from us, and for all that I would like to express him my greatest admiration, sympathy, and admiration for his work and friendship. I wish you the best for the years coming now. I'm sure you will be very busy, Masahiro, and that all you will do will be appreciated by your colleagues and friends and family, of course. Thank you again, and have a very, very happy time now. Bye-bye.
Well, Masahiro, I never thought that the time of retirement will come so quickly. We are fortunate to be, as chemists, to be paid to do a job that in fact is like playing, and it's very enjoyable. And so it has been fun life for both of us, I think. And one of the good things about being a scientist is that you get to know so many people all over the world, initially from their work, without actually seeing them. In your case and our case, it's the synthesis of terpenes. And so we have met several times in Japan, and you have visited us at least twice in France. And I remember on one occasion when I had to collect you at the train station, we could not meet because you came out from one exit and I was waiting for you at another place, because as it happened, the TGV at Massy-Palaiseau could arrive at two very different locations, which were quite far apart. And it took us a while to ultimately find each other. And I remember that Katsuko was with you. And in the evening, we went to have dinner, and Katsuko and you wore the traditional Japanese dress, which was very impressive to me and very impressive to the other people in the restaurant. They had never seen anything like it. So it was a very memorable evening we had. So, well, I hope we will have a chance to meet again. Travel at the moment is difficult, but hopefully this pandemic will be overcome and we will be able to meet again. Thanks to you, I had a very enjoyable experience, teaching experience in Japan. And so we could spend, Lydia and I could spend a couple of weeks living like Japanese people and cooking Japanese food, and also going to different restaurants. It was a very, very lovely time we had. So your friendship has been very important to me, and I hope we can continue fostering this friendship for many, many more years. I wish you all the very best, and I wish you a long life to both Katsuko and you. Take care.
Hey, Masahiro Toyota, 丰田增运. So what is a better time to congratulate your retirement and celebrate your retirement other than Chinese New Year? 恭喜發財，恭喜發財啊! As we always said, chemistry is not only everything, it's the only thing. So I'm so glad to be a friend of you, to work with you at Columbia. And we are so energetic, and this is the year of the ox or cow. So we shouldn't retire, and we should be able to, we are just energetic. Today, I rode 80 kilometers to dedicate for your retirement. Oh yeah, nobody knows who I am probably, but that's me. Oh, whoa. The 拼湊team. So work together at Columbia. I'm so honored, so glad to know you. Just hope you have a happy retirement. Stay in chemistry. Be energetic. Let's do it, man. Let's be a cow.
It is indeed a great pleasure for me to take a couple of minutes to congratulate my good friend and scientific colleague, Masahiro Toyota, on the upcoming retirement. And I just want to say a few things, give you some background. So I first met Masahiro about 35 years ago when I joined Columbia University in Professor Gilbert Stork's lab as a postdoc. Masahiro had already been there for a couple of months and had already established a reputation as being one of the really gifted synthetic organic chemists in the Stork group. At the time, he was working on a really classic landmark natural product called reserpine. And he had devised a very clever, elegant synthesis of the key core component of reserpine, the 6-membered ring, so the cyclohexane ring with 5 adjacent chiral centers, contiguous chiral centers, by taking advantage of a double Michael reaction that was, of course, endo and diastero selective. Toward the end of and he completed that synthesis, I should say, and really represents one of the truly clever and elegant synthesis of this natural product. Toward the end of his stay there, he started studying palladium chemistry, and with the plan of using palladium chemistry for solving certain structural problems in his independent career, and he went on to do just that. But before I talk about some of the work he did, let me just mention that Masahiro is of course one would know that from the many impressive targets he has completed, but Masahiro is a determined and competitive man. And so we used to play tennis together and had great fun. An indication of the competitiveness that he had is the fact that he referred to himself, in fact, what he would say is, "I am Lendl, you are Becker." And the reason he said that is because at the time, Ivan Lendl was the #1 ranked tennis player in the world, and Becker was #2 or 3, which to me was high honor to be considered 2 or 3 or even 100. But in any case, we had good time playing tennis during our stay at Columbia University. When I first visited Masahiro in Japan, he also showed me his love of powerful cars. And so he had this souped up Nissan, which he had modified so that it became even more powerful, had something like 600 horsepower engine or so, could go well over 150 miles an hour, maybe 200 miles an hour. And sadly, he couldn't take full advantage of it. But anyway, he'd like to refer to that car as the monster. And it certainly sounded like a monster. With regard to the science that Masahiro has done over the years, it's really outstanding work. And in fact, he has worked on a broad range of natural products. So he took advantage of palladium chemistry to solve some challenging aspects of terpenes. He completed the synthesis of hirsutine, acetylcholine, a number of members of the caurine family, as well as the gibberellins. He took advantage, very clever advantage, of a reaction that he had seen when he was at Columbia University, the cyclopropyl carbonyl rearrangement. He has worked in a number of other compounds. In fact, there are a couple of natural products that we've both worked on, and so we have that common interest. One of them is metalamide. I was happy that the student that worked on metalamide, Natsuko Kugawa, went on to do a postdoc with me and enjoyed having her in my group. He also worked on well-wittendonones and reported a very elegant and just remarkably efficient way of constructing the core bridge bicyclic skeleton of well-wittendolinone. Well, what I would say is that, Masahiro, you're a good friend, and it's really been a pleasure interacting with you, sharing chemistry with you, and I hope the retirement brings you a lot of joy and satisfaction, just as your professional career has. I hope, most importantly, that we continue to get together and meet on a regular basis. And I certainly look forward to the next time we are able to get together. All the best to you, my friend.
Konnichiwa. I'm here to say a few words about Professor Masahiro Toyota. My name is Frederick West, and I have known Toyota Sensei for almost 35 years. I'm sending this message from Edmonton, University of Alberta in Canada. This is a view of our campus. Here's another view, and you can see here where my office is, which is right here. Of course, all of these photographs were taken in the summertime, and if you know where Edmonton is, you know that it does not look like this in the winter. It looks more like this. In fact, it's minus 20 degrees Celsius today. How do I know Toyota? Well, I know him because we are both part of the Stork family. That is, we both worked for Professor Gilbert Stork at Columbia University. This is Havemeyer Hall, where Professor Stork's labs were located. I arrived in New York in 1986. Toyota was already there, and he was working on the total synthesis of the alkaloid reserpine. Here's the structure of reserpine. He worked very hard on this, but the paper did not appear until 2005. This is very common in Stork's group. Sometimes postdocs have to wait a long time before their research appears in the literature. Toyota-san worked in the same laboratory as I did, and I quickly discovered that he was very intense. His desk was right next to mine, and our fume hoods were also very close together. So from this, I was able to see that he was the hardest worker in the Stork group. When he was sitting at his desk, Toyota would usually write in his laboratory notebook or read the chemical literature, but sometimes he would turn and talk to me, and he would ask me questions. Sometimes the questions were about chemistry, sometimes they were about geography or American history, and sometimes he would show me something that he thought was interesting, that he thought I should know about. One time he showed me this paper, which is about a very interesting photochemical reaction, which is summarized here. Now, he didn't show me the mechanism of this reaction. He just showed me the transformation and told me he thought I should think about this and figure out how it happened and whether it was interesting. So that paper showed the mechanism. I eventually found it. It was quite elaborate and difficult to understand, but very, very interesting and full of possibilities. And I ended up taking this chemistry and using it in one of my proposals when I applied for academic jobs. And that proposal I ended up trying, and it worked. And this ended up producing quite a few publications for me early in my career. And it's all because Toyota showed me this chemistry. So after about a year, Toyota returned to Japan, and I didn't see him for a while. And then I started my first job at the University of Utah. And after about 10 years, I had the opportunity to visit Japan. And one of the places I visited was Tohoku University, where Toyota was an associate professor. And I was very happy to be able to resurrect my friendship with him. And this is a picture of us sitting together and a picture of us going out to dinner with my host at Tohoku University. After that first trip to Japan, I was able to visit Japan a number of times, and usually I tried to get together with Toyota. Here's in 2007, he arranged for me to be a featured speaker at the annual meeting of the Pharmaceutical Society of Japan. And this is a picture at a soba shop in Toyama, where the meeting was held, along with several other people, obviously Toyota. This is Professor Murakami, and this is Professor Varesh Rawal, who was also in the same laboratory in Stork's group, just sitting one desk over from Toyota. Then in 2009, Toyota Sensei invited me to spend several weeks at Osaka Prefecture University, where I presented several lectures and spent a lot of time with his research group. And then at the end of that, my family came out to visit me, and spent some time in Osaka and some time in Tokyo. And while they were there, my middle son, Peter, became very, very obsessed with takoyaki. And he even learned how to make it and took home some equipment for making it that Professor Toyota purchased for him. And he made takoyaki for us for many years. This is a photograph taken in Toyota Sensei's office with my family, and also Kazuko-san and her cousin Eiji. In 2012, I was very happy to be able to host Professor Toyota on a visit to the University of Alberta, where he gave several lectures and visited with my research group. And then after that, we visited the Rocky Mountains. And this is a picture of him and Kazuko-san at Athabasca Falls, which is in Jasper National Park, which is about 3 or 4 hours away from Edmonton in the Canadian Rocky Mountains. Professor Toyota has done a lot of really excellent chemistry that I would like to talk about, but he told me that this has to be a very short presentation. So I'll just mention 2 papers that I especially like. The first one is total synthesis of gibberellins, and the second one is total synthesis of mycalamide A. And both of these papers are really excellent with the way that bond formation is controlled and stereochemistry is controlled. And it shows a very, very creative understanding of the reactions of organic synthesis. So I was actually very surprised when Professor Toyota told me that he was going to retire. To me, it seems like he is still very young. And I know he still has lots of scientific ideas, such as artificial intelligence in organic synthesis, and I hope that he will pursue those ideas. However, I just want to emphasize that in his career, Professor Toyota has been an extremely creative researcher, an excellent teacher, a thoughtful mentor, and most important to me, a great friend. So I just want to wish Masahiro all the best in his retirement and congratulate him.
I'd like to express my sincere gratitude to the professors shown in this slide. I worked for Professor Kametani when I was an undergraduate student at Tohoku University. He published 1,201 papers. It's amazing. I received my PhD degree from Tohoku University under the guidance of Professor Fukumoto. He was very tough, but I liked him very much. Professor Ihara gave me a lot of suggestions about not only chemistry, but also many things. After moving to the US, I worked for Professor Gilbert Stock at Columbia University as a postdoc for 2 years. I completed the total synthesis of -redapine there. Professor Stock was a genius. He knew almost everything. He was a walking sci-finder. Professor Il-hyun Ryu asked me to join Osaka Prefecture University. He was so energetic about international exchange that I was very influenced by him. Finally, I'd like to express my sincere appreciation to all my students. This slide shows the title of my final lecture, Computer versus AI in Organic Synthesis. Kan means intuition in Japanese. So first of all, I'd like to talk about a couple of syntheses using computer. And then I'd like to discuss AI-assisted syntheses. This slide shows my representative synthesis using computer. This target molecule has a bicyclo 222 octane ring system, which could be synthesized from this bicyclo 321 octane ring compound using radical rearrangement. This substrate could be prepared by our non-synchronous intramolecular Diels-Alder reaction of this tetraene compound, which could be obtained from this bicyclo 321 octane by our stereoselective 1,4 addition. This bicyclic compound could be assembled from this optically active silylenate, which could be available from this ketone. We used D'Angelo's protocol for the synthesis of this compound. The optical purity of this compound proved to be very high. This compound was transformed into this cyclohexene by 4 steps. Regioselective oxidation of this compound was conducted using a catalytic amount of oxidizing agent. After preparation of the corresponding silylenate, the first key reaction was performed using palladium catalyzed cycloalkylation to give the desired bicyclo 321 octane in an 83% yield. After isolation of this product by flash column chromatography, the dienophile part was introduced from the convex side of this enol. After reduction of this ketone followed by thioimidazolide formation, we attempted to change the structure of this bicyclic compound using radical rearrangement. And it was found that the radical reaction of one of the stereoisomers competed with syn elimination to produce a byproduct. So we decided to install this radical rearrangement process as a final stage of this total synthesis. The diene moiety of this tetraene compound was constructed by totally 7 steps from this ester. An intramolecular Diels-Alder reaction of this compound was conducted at 200 degrees Celsius to give the desired perhydrophenanthine derivative as our major product. This major product arises through this favored conformation. The separation of the 2 isomers was very tedious at this stage, but it was found that the desired isomer synthesized by 2 steps was easily separated. Stereoselective methylation followed by hydrolysis provided the ketone. Finally, the target molecule was obtained using radical rearrangement. So far, we completed the total synthesis of these natural products using the same protocol. After moving to Osaka Prefecture University, we started the total synthesis of gingolite C using palladium catalyzed cycloalkylation of ketene silane acetals. This slide shows 2 different approaches toward gingolite C. As shown in this slide, only 21% of the desired compound was obtained using this ketene silane acetate. Even when this ketene acetate, which is expected to have a Thorpe gold effect, was used, only 20% of target molecule was isolated, together with its isomer. Ketene acetates, which are highly sensitive to acids. Therefore, they are unsuitable for the palladium-catalyzed cycloalkylation reaction conditions. To solve the problems mentioned in the previous slide, we decided to investigate the cycloalkylation using beta-ketoesters. It worked, and about 80% of the desired bicyclic compound was obtained. We called this reaction the second generation palladium catalyzed cycloalkylation. We can apply the second generation palladium catalyzed cycloalkylation to this beta ketoester and bicyclic lactone ester like this. We examined the substrate scope, and it was revealed that hydrogendanes can be synthesized as a mixture of double bonds. We decided to synthesize pumiliotoxin C using the second generation palladium catalyzed cycloalkylation as our key step of this total synthesis. Pumiliotoxin C was isolated from this brightly colored frog. Central nervous system will be paralyzed by this natural product. By the way, do you know the reason why tropical creatures have bright colored? If you find it out, please let me know. It must be very interesting. He is neither my father nor my grandfather, but some people catch animals on trees using blowguns with pumiliotoxin C. Actually, I have my own blowgun. Here. I bought this stuff in Bali Island in Indonesia. I paid only $10. And I kept practicing this stuff to wake up the sleeping students during my classes. Of course, I used caffeine instead of pumiliotoxin C. No, he's kidding. This slide describes the retrosynthetic analysis of this target molecule. This cis-hydroxydane could be prepared by the second generation palladium catalyzed cycloalkylation. The stereochemistry of this trans isomer was controlled by 1,4 addition. The key reaction was conducted with a catalytic amount of palladium acetate to give this hydroxydane in about 80% yield. This product was transformed into this ketone by 3 steps. After conversion of this ketone to this hydroxydane and isomerization, the resulting ketone was transformed into this lactam through Beckmann rearrangement. The immediate formation followed by Grignard reaction and hydride reduction gave the target molecule as a single stereoisomer. The stereochemistry was controlled by the C-Plaque effect. Additionally, we, or I, have completed the total synthesis of plus micalamide A and minus rezapine. The evolution stage of organic synthesis is now almost at the top. Some people jump and reach the merge their mother country, according to John. On the other hand, what about the evolution stage of AI? Probably we are now here because many appliances equipped with AI are available. What happens to the evolution stage of AI in organic synthesis? We are still baby. Do you know the reason why? Before that, let's have a look at that historical background. This slide shows the historical background of AI-designed synthetic programs. More than 50 years ago, Professors Corey and Whiskey developed OX for the first time. 3 years later, OX evolved into RASA, but this system was too difficult to operate for even experts. At the same time, Professor Burson reported an idea about a user-friendly automatic chaos. These systems are called chaos and are short for computer-assisted organic synthesis. In 1980s, Burson and Sumitomo Chemical Company reported SynSap as a prototype of automatic chaos. You can see a quite number of chaos, but most of them are not practical, except Chematica. Many papers concerning about new prototypes have been published, but they are not practical because there is no paper that evaluates the proposed synthetic routes through demonstration experiments. One of the reasons is that it takes a long time to experimentally evaluate proposed synthetic routes using AI. In 2008, we joined the SynSap development program. We decided to make novel reaction rules through our own experiments. More than 1,200 novel reaction rules have been recently installed on SynSap, so it's possible for SynSap to propose synthetic routes containing creative reactions like human experts do. From this slide, I'd like to show you our recent results about SynSap-designed total synthesis of bioactive molecules. This slide represents the structure of the first target molecule. This target is known as a cholesterol absorption inhibitor. First of all, we have to draw the structure of the target molecule using CMVEdit and send this file to the server of SynSap by email. In 1 minute, we received many synthetic routes for the target molecule with the default settings. Unfortunately, we cannot find interesting approaches. To avoid classical approaches like amide formation or 2+2 cycle addition, we used an option, in this case, start with option, and did the second run. In this case, SynSap proposed an interesting route which has novel stereoselective formation of trans-beta-lactam ring system. This slide summarizes SynSap designed synthetic route. To make this substrate much more durable, we changed this part to ester group We spent a lot of time to find out appropriate reaction conditions, and eventually 75% of the desired trans-beta-lactam was obtained. This slide shows a possible reaction mechanism. After activation of this carbonyl group, followed by hydrogen abstraction, this TMS imidate was formed. Further activation and hydrogen removal gave this unsaturated ketene silyl acetate, and this target molecule was obtained via 4-pi electrocyclization and hydrolysis. Obviously, the two substituent groups are trans to each other. We succeeded in the total synthesis of SCH 47949 as proposed by SYNSAP. Kinamycin D is known as an anti-cancer natural product. However, this mimic exhibits stronger anti-cancer activity than this natural product. So we searched synthetic routes of this compound using SYNSAP. This slide shows SYNSAP proposed synthetic routes for the mimic. We focused on this synthetic route and set about the total synthesis. This slide summarizes the SYNSAP proposed route. The key step is this catalytic cyclization. After repeated studies, we found a catalytic method for the construction of this biphenyl compound, and we finished the total synthesis of the target molecule as proposed by SYNSAP. This slide depicts the structures of 3 bioactive benzofurane derivatives. We assumed this compound as a common synthetic intermediate for the 3 targets. We searched synthetic routes of this compound using SYNSAP. We were interested in this synthetic route and started our studies. This slide summarizes the SYNSAP proposed route. The starting material is acyclic compound. It is very interesting. To our surprise, the target molecule was obtained in one step from this acyclic compound. We succeeded in the improvement of the chemical yield of this target molecule using a different route. During the examination of the solvent effect of this reaction, we discovered an orthogonal synthesis of this benzofurane analog and this bicyclic compound. We succeeded in the total synthesis of target molecules as proposed by SYNSAP. It is safe to say that SYNSAP is now the most sophisticated chaos all over the world. The evolution stage of SYNSAP in organic synthesis is here. The level is similar to junior high school students, so we still have a long way to go. Around 2050, Professor AI will have a laboratory, and his PhD student, Mr. Perfect, will be working for him without sleeping. So what should we do in the future? You got to think. Good luck. Did you enjoy my final lecture? Great. I wish you all the best. I will see you someday. Bye now.